Good morning to everyone. And that was Dire Straits. And Ernie, what was the title of that one? How Long? That seems appropriate. Now, in terms of what's being returned, the quizzes from Friday are being returned. And I have some tests up here for those of you who weren't here on Friday to pick up at the end. So remember to do that, please. And we had homework on 5-4, was that it? That you were finishing up. Is there any question on the homework on 5-4? Okay. So section 5-4, what problems? Which one? Number 11 and 5-4. Let's see what we have there. Get to the right page, number 11. Now this is, I have a hunch. Are you talking about the computer problem 11? Okay, I have no idea which one that is in the book. What is it now then? 18x to the third to the fifth. 2w to the fourth, z,
divided by negative 81,
divided by negative 81, x cubed, okay,
over 6w squared,
z. Does that do it? Okay, so this is one of the problems from the computer homework, number 11. What's the first thing we want to do? Invert, flip, reciprocal, all come out the same way. So 18x to the fifth, a 2w to the fourth, z to the first, then a dot rather than an x, a negative 81, x to the third, over 6w, oh, hold it, help if I inverted it, I didn't. 6w to the second, z to the first, and then the negative 81x cubed. Inverting it. Now we should be in business. Okay, so at this point, intermediate steps. You have an x, a w, and a z. So I'd like to see something like this, an x to the 5 minus 3 down here, a w to the second minus the 4, and the z to the 1 minus 1. Then for the part where we're reducing, first a comment, we will have a negative out in front. The 2 would cancel here, giving you a 9. The 9 cancels here, coming down here for a 9. So it looks like this is over a 9. That would be my intermediate step. And I think I'd probably put this minus sign a little bit closer of the entire fraction. And so the form that you will want in the book or on the computer before I answer questions is going to be minus. Then you're going to have x to the second. You have z to the 0 over 9 w squared, which then becomes negative x squared over 9w squared. Robert.
when you do that first cross cancel, the 2 and the 18,
Yes.
I thought you were only allowed to go diagonal.
When we cancel, if we think back what we did in Math 10, we said sometimes you will be given a fraction that should have been reduced and wasn't. And there were many times in the Math 10 problems where you had to reduce something within a fraction of its own. So, Ernie, if I can have just a little more there, that you would have to do this. This was something we'd done before. If things are given to you reduced, then all you'll end up doing is cross-canceling. But we always have to be alert to the fact that this may not have been reduced here. Any other question? Kim?
Shouldn't it be a 2 over there for the 18s? Yeah, but 9 goes into 18 twice, 9 goes into 81
But I first had 2 into here and 2 into here. So I canceled this 2 out, giving me a 9 up. Pardon? Yes.
And then you use the 9.
The 9 from here to go into the 81 here and get 9.
And the 6 just stays, but you didn't do anything with it.
The what now? I didn't see to put the 6 up there, did I? I didn't pick that up, so I should have gone what? 3 into there for 2, and I thought I was done, slipped up on that. So this is going to be what? 2 here with a negative and a 3. I just didn't pick up on the 6 there. So this is going to be what here? I would have a negative 2 here and a 3 here. And then finally, in its simplest form, this here. Thank you, Natalie. Okay? Any other questions there? Okay, any other questions in 5-4? Sandra?
It's problem number 38 in the book.
38 in the book. Is there a question on this before I leave it? Okay, let me put up here 38 next. Okay, Shamra.
My question is, even though the z is to like the 0 power or whatever, do you have to put that z in there?
I would like as an intermediate step to emphasize that when you subtract the exponent, you're going to get z to the 1 minus 1, which is z to the 0 power, which is 1. Now, again, this depends when we're talking about the problems. As we go through them and you're trying to practice, I think that's an important step to do. Later on in a test, you might not want to fool with that and just immediately go to a 1 there. But I do want some intermediate step. And the thing I'm concerned about, when you get a z to the 1 minus 1, you don't suddenly say, well, that's 0.
Right.
Z to the 0 is 1, and that, to me, was an important thing to remind you about.
So you wouldn't put it in the answer, though? You wouldn't put your z in the
No,
answer?
because once I have z to the 0 here, then this is going to be a 1, and there's no sense of putting the 1 in there,
Okay.
because 1 times 2x squared will be 2x squared. Does that cover that problem now?
Just one more thing.
On this problem still, okay?
I was struggling to see if the 81 was negative. Then how come our 2 is negative?
The negative can go in 3 different places. It can go in the numerator, it can go in front of the fraction, it can go in the denominator. So I put this just when I made the comment that since I have a positive times a negative expression, I'd have a negative out in front. And so I kept it out in front. Technically, it's down here. If you said I have 2x squared over negative 3w squared, that would technically be correct, but we try to avoid the negative sign in the denominator. Anything else on that particular problem? Okay, Sandra, number 38 in the text. Okay, that's a mess, so let me write what's there. Number 38. So I have a negative of the entire fraction, and I have 13h to the 6th. Is that correct? And that's over 20hk? I would prefer to put 1s in there as I write it down. And then I have that divided by, and then in parentheses, a negative 65 h to the 3rd, k to the 1st. Is that correct? And then that's over a 25k squared. Now this brings up a point right out of the gate, coming back to, Robert, what you were talking about, whether or not you can reduce within the fraction itself. The fact that I have a k to the 1 and a k to the 2nd, I'm going to probably want to simplify that right at the beginning. But before I do that, let me rewrite it as a multiplication. So a big dot and a 25, k to the 2nd, over a negative 65, h to the 3rd, k to the 1st. Okay, the first observation, this time I'm going to have a positive. And here's a case, Shamra, where I have a negative here. The negative in the original was for the entire fraction, but that, in this case, would be a negative of this fraction, so I'm going to have a positive at the end. So there's no sign to worry about. In terms of simplification, the 13 and the 65, so the 13 cancels here, giving you a 5 here. Whether you see the 20 and the 25 next, I don't know which. I prefer probably to do this and then cancel the 5 coming down here to 4. So I don't mind seeing that in that step, but I don't want to deal with some of the confusion that occurs starting to work with the exponents there. So I would like to see this as h to the 6 minus 1 over k to the first times, and then I have a k. Let's see, I guess I have 4 there, right? 4k to the first. And I have a k to the 2 minus 1 over an h cubed, just to try to get some things simplified. So I'm simplifying each of these fractions after reducing the numerical part. Robert?
Where did you break down the 13?
13 and the 65. 5 times 13 is 65. Kim?
You're subtracting from top to bottom here?
Well, I had an h to the 6th over h to the 1st, so I subtracted the exponents. So the next step, just to try to simplify, I have h to the 5th, k to the 1st, over 4 k to the 1st, h to the 3rd. So that's going to be h to the 5 minus 3, k to the 1 minus 1 over 4. And I'm just trying to do this in a way that minimizes, hopefully, the kinds of careless errors that I see in the quizzes and the tests and the things I have to be careful of also, because it's awfully easy to lose something here. So this becomes h squared, and this is k to the 0, and this is, of course, that'll be a 1, and then this will be a 4, so I believe we get h squared over 4. Now, whether or not you rewrite this as k to the 0, I don't want to make it too tedious, but the key here is try to not get it so chaotic that when you look at it or I look at it, I can't follow what you did. And for those of you who want to do it all in this step, it is really difficult for me to follow what you've done, and I would challenge you to go back and look at it a day later and see if you can figure out what you did. Whereas here, I can start seeing my logic as I go through, and I can catch errors, perhaps. There are so many little places to miss a sign, to miss an exponent, like putting the 1s in here, that I think very critical to do. You have to be careful with that. So aside from Murphy's Law, which says if something can go wrong, it will, to come through these completely clean and not make some careless error, it's a little bit like in the quiz from Friday. There are a lot of places where just a little error, and depending on how early on it is how much credit you get for the problem. But any other question on number 38? This is the one Sandra asked about. Okay, there were a couple other questions, and who else had a question? Ephraim? That was from 4-4? No, I'm not going to do a problem for 5-4. Okay. And it is? 3 okay. 3 1/2. Okay, and this is the one I mentioned. This comes out of what we'd done earlier. You rewrite it first, and then you invert and multiply. And the only thing that's going to reduce is that, so you get 35 over 23. You have an option at that point of doing what? Well, the estimate part, this is about 3, and this is about 2. So 3 divided by 2 is about 3/2, which is 1 1/2. Okay, this one's going to come out 1 12/23. Well, am I close? 12/23 is about as close to 1/2 as you can get. We need 12/24. Okay, so again, the idea of estimating, I'm rounding off. You might have argued 3 1/2 should have been rounded off to 4. And 4 divided by 2 is going to give you a 2. And I'm not quite as close on my estimate. So, but again, it's just an idea of trying to be in the ballpark. And the only justification I really defend in terms of the estimates, so that when you see problems and you're doing mental arithmetic, you have an idea if you're in the ballpark or not, because it's something that I don't think your backgrounds, generally speaking, focus on. You do a problem and you're not sure just what the answer should be. This is something that we try to get around with scientific notation. So if you think of this problem in terms of scientific notation, this is 3.5 times 2.3. Okay, and so they're both in scientific notation the minute you do that. But the general idea, when in an earlier lifetime, it's slide rule life. Okay, before the calculators became ubiquitous in the late 1970s, you had to try to estimate where your decimal point would be. And that was the point of the estimation. A kind of double use of the word point there. So if I knew this was going to come out somewhere around 1.5, and all I could read on the slide rule was a 1.5, I knew it had to be 1.5. You located a decimal point that way. The defense for what we're doing here isn't quite as clear as it would be in a stat class where we're forever looking at formulas we substitute in to try to get some sense of what the answers should be. And let me give you an illustration of what I have in mind there. If I go ahead, as in a problem that we did this morning in class, we had a 28, and it was 28.5, I guess, rounding off, and I had a 21.7, and I had it over a 10.98 over the square root of 30. Okay, now that was just a calculation we had to do. And I wanted the class to understand what that was approximately equal to. Well, the square root of 30 is roughly 5.5. Now, if you remember our rule for squaring 55, you go 5 times 6 and put a 2.5 after it. So it would have been 30.25. So 5.5 is a pretty darn good answer here. This is about 11. 11 over 5.5 is about 2. 2 goes into something up here that's close to 6, or 7, I'm sorry, and I have something that's close to 3.5. And that's what they needed to do in class. So again, 28.5 minus 21.7, that's about 7 up here. This part here, we were to estimate at 5.5. Well, 10.98 is for all practical purposes 11. 11 divided by 5.5 is a 2. So that whole mess down here is a 2. 2 goes into 7, 3.5. The problem with this is that students using a calculator don't know how to handle that square root properly. Now, what I told them today as we looked at that problem is you have 7 divided by a fraction. You invert and multiply. So in essence, it's 7 times 5.5, which is close to 40, okay, in the sense that if this is 5.5 and that's 7, you have 35 something. And then it's divided by 11, and so we're going to get something between 3 and 4. If you do this improperly, and you take 7 divided by this, you get 7/10, and then divide that by 5.5, you get a ridiculously small answer and screw it up. So this ability to estimate here becomes very critical to avoid errors that come out of using a calculator. That is why the estimate is a valid thing to consider. Michael?
Would there be any time that we would have to learn how to use a slide rule?
At this point, learning to use a slide rule would be something entertaining, and you'd gain an enormous understanding of scientific notation, and you would gain a very important background on reading scales and having to think. And those processes, I think, served students much better than pressing buttons and not having any sense at all of what you're getting. And so I could defend not because of the speed, although you can do things in a slide rule very quickly, nor on the educational value up, what appears to be a superficial value. But if we look at what you learn, there are an enormous number of benefits to working with a slide rule, and I have absolutely no regrets that I spent the first 5 years of my life as an engineering student and math student using a slide rule. I think I gained an enormous amount. And the tables that we look at in the back of a book now, we had to do on a slide rule, and we had to look at those tables when we because a slide rule is a bunch of logarithms. It's a bunch of exponents. And so you can get those from tables, you can get them from a slide rule, and you had to get in between values. So you play games of halvesies and so on, called interpolation. Those are skills that are just totally lost at this point. And I think to the disadvantage of most students. Same with what we call trigonometry. Our calculus students have really some pretty poor backgrounds in those areas because they've depended so much on technology, they don't have conceptual understanding. So there'd be something to be gained for a slide rule, but you'd find very few people wanting to suffer through what goes with learning to do that. Any more than an abacus, you could argue, is a very fine way of doing a lot of computation, but most of us don't want to spend a lifetime working with an abacus, so we get faster than a calculator. Other questions on the homework? That was answering Ephraim's. Anything else out of 5-4? Okay, if that's the case, let's move on to 5-5. Now, the request has been made in terms of opening up any of the computerized homework. I have one request, and if you have others, let me know. 5-4? Okay, that's the one that we still are working on. Okay, I'll open that back up. I have 5-5 scheduled for tomorrow, but we'll see what happens. Let me now go back center, Ernie, and we're going to look at section 5-5. 5-5 gave me some real nice feelings as I looked at it, because what is done is, I hope, an extremely familiar process with what you did in 10. Find the LCM using prime factoring. Here it's called prime factorization. Same argument. When does an LCM become an LCD? When the numbers are denominators. So nothing is new in this process. It is the same old thing. And what I did like about this is you even talk about doing a least common multiple by listing. Okay, and this was the problem illustrated at the very first part of this chapter. I'll bring that down a little bit tighter. But if we were wanting to find the LCM or LCD of a 6 and a 4, if they were the denominators, you can immediately see the common 12 as the least number, and that's, of course, what we did before. And we said that works fine unless you have what? Some very big numbers, and your LCD or LCM comes out in the 400 range, and a half hour later you're still trying to do it. So there's absolutely nothing in this first part of this presentation in 5-5 that is any different than what we did in what we called, I believe, the 6th review in Math 10, where we did prime factoring. So the only thing that gets a new wrinkle here is on page 347, where we're going to get monomials involved. So let's look at this. I have 18x cubed y and 24x z squared. Ernie, I'll need camera 2 on the sideboard, if you wouldn't mind, please. And there's nothing here that is particularly different than what we've done before. I believe I have some chalk over here. 18x cubed, and if you play the game with exactly the same rules, it should be very comfortable. And 18x cubed y to the first, and I have, let me write the other one down and then we'll cut to here, 24x to the first z squared. Now I want to find an LCM, just like it would be an LCD. So I'm going to write the 18 as 2 to the first, 3 to the second. And I'm hoping we're at the point where you can do that in your head. 18 is 2 times 9. 9 is 3 squared. And then I have here x to the third, y to the first. The 24, okay, if you think about that, 8 times 3. 8 is 2 to the third, 3 to the first, x to the first, z to the second. Now I'm assuming that this part here is at least doing the 18 and the 24 straightforward. Are there any questions there before I move on? Because if you're comfortable with that, how did I find whether we called it an LCD or LCM? We said you write down every prime you used. Okay, so we had 2's and 3's. But this time, any variables you see, which would be x, y, and z. Pardon?
Without the exponent?
Without the exponents for the moment. Now, what did we search for before? The highest exponent we had. So on 2, I have a 1 and a 3 as an exponent, correct? So the highest was 3. On the base, or the prime of 3, I had an exponent of 2 and 1. The highest is a 2. On x, I had a 3 and a 1. I'll use the 3. I have a y to the first and a z to the second. Same process, bless you. That's quite a collection of things you're sneezing at. Cheetos, donuts, and something, a drink. Okay, is this breakfast, Nancy? No? Okay. We're just telling everybody watching what people eat and exist on in Modesto. Okay, so what does this become here? An 8, 9, so 72, x to the third, y to the first, z to the second. Got it?
Yep. I like that.
Now, let's say, just for the heck of it, that I just had this originally as a denominator. I had the reciprocal of what I had there. And I wanted to change it now to this new denominator. Remember how we talked about this before? I said you look at what you have and you look at what you want. I had an x to the third, I had a y to the first, but I want a z to the second, so I'll have to multiply this by z to the second. I had 18, or I had maybe rephrased that. If I look at what I have here, I need to slide over just a bit, Ernie. I had a 2 to the first, and I wanted 2 to the third, correct? So that means I'd have to multiply by 2 to the second to get my 2 to the third. I had 3 to the second, and I had an x cubed, and I had a y to the first, so all I needed was what? The 2 to the second and the z squared. So I multiplied top and bottom by this much. So my answer here is going to be 4z squared over that. You usually do this. This is the new denominator. Here's my old denominator. So you divide. Correct? And you say 18 into here, and that goes 4. These cancel, and you're left with 4z squared. Now what I'm saying instead, coming over here, here's the denominator I had, here's the LCD I want. Now compare. How are they not alike? Sesame Street time. This one has 2 to the third, but I only had 2 to the first, so I need what? 2 to the second. There was a difference in this and this. Now these parts, 3 squared, x cubed, and y to the first are all the same. This I didn't have. So I didn't have 2 to the third, I had 2 to the first. So if I multiply by 2 to the second, I'll have 2 to the third. And if I multiply this by z squared, I will have the LCD. So you can avoid the division I'm showing here as we slide over by just making a comparison. And we played that game in Math 10, and we change a fraction to a new fraction with the new denominator. And that's what we're going to be doing in this section also. Okay, so I'm going to leave that on the board here, and I'm going to go back up front. Now, one of the nice things that I like about what's being done in the book and where we've been before, the first half of nearly every section in Chapter 5 is familiar. We've been there before. It's the last part of the problems that will cause you some stress or distress. So let's see what we can do in the fourth objective down here. And it says write fractions as equivalent fractions with the new LCD. That's exactly what I just illustrated. However, they're going to be a little more complicated. So if we look at something like, I'm trying to see what I want here, and I don't like what I'm seeing, but let's just look at, this one's ridiculously easy. I want 24x squared as the new denominator, and I had 5 over 6x squared. So what you could do is do this division down here they're showing. Let's see, where is it? I thought it showed a division there, and I'm not seeing it, so let me come back up to here. If this is the LCD I want that I'm pointing to, and this is what I want, you just divide 6x squared into 24x squared and you get a 4, correct? So I'm going to need a 20. Make sense? Does it make sense? Okay. This is sometimes where my perception of what should be easy and your perception of what is easy don't always match. Here's the original. Let me write it down first, Ernie. Okay. I want a new fraction with this denominator.
I got the 20 part.
Okay, but you take 6x squared into here, and you get 4.
Right.
So you multiply here by 4 and here by 4. Oh, I hate putting the x's there, sorry. Does that make sense now?
Yeah.
And now we just have 20.
Right. Okay.
What was messing you up?
I didn't know how you got 20.
Yeah.
Oh, 4 times 5. If I do 4 down here, I've got to do it up there. Basic principle of fractions. Lest we forget. Okay, back to the document, Cam. Okay. The basic principle of fractions, the BPF. Okay, not much enthused with that. Let's try coming over to something more fun. Number 50. Not yet, Ernie. I need to block something off here. And block this off. Okay, I think we're about ready. Let's try it. And I need to flatten that out, I guess. There. So I have this problem. And I'm unfortunately, let's see, come off there for a moment. I've done something good and I've done something bad. I need something that will not manage to block the light. Okay, let's try that. That's a little bit better. Nothing that a good hardcover book wouldn't solve. Okay, let me write down these two. Now this is more in the spirit of where we need to be if we're going to work with monomials. We have two monomials that are rational expressions. And let me write out the word and this time. C over 30ab squared. And now, as I do that, what am I going to want to do with some exponents here? What would be your recommendation? Is that, that is a 30A. That's what's the problem. Thank you, Ernie. I thought I had just written an A twice. That's what bothered me. AB squared, if I got it correct now. Okay, thank you. Okay. What do I want to put in there? The ones that are missing, the exponents. If you're going to be finding LCDs, you want exponents on everything. So that's going to be A to the first, and that's going to be B to the first. Next step, I'm getting a frown. I'm going to write each denominator in prime factored form. So the 24 we've already done. That's 2 to the third, 3 to the first. A to the fourth, B to the first. Here, the 30, 2, 3, and 5. 2 times 5 is 10. 3 times 10 is 30. So 2 to the first, 3 to the first, 5 to the first, A to the first, B to the second. Any questions there? Marisol? You sure? Okay, because your expression doesn't go with the, don't have any questions. What are the primes I see here? 2s, 3s, 5s, A's, and B's. So 2s, 3s, 5s, and A's and B's. Now what do I search for? Highest exponents, correct? So on a 2, I have a 1 here and a 3 here. So my highest exponent is a 3. I have a 1, 4, 2. Now 3 of you are in agreement. Do the rest of you agree? Natalie, was that yes? Okay. Anybody with a question? Now just to get the LCD, we would expect to see something here where you multiply all this out. So this is an 8, and 8 times 5 is 40, times 3 is 120. A to the fourth, B to the second. Now let's go back to the problem. Am I supposed to find those as new fractions now? What did the directions ask me to do? You don't see it there, but somebody tell me as we come off there. Okay, so we have to write each one of these as a new fraction with the LCD. We've been there before. This was one of the lessons we did as a review in Math 10. The only thing we've added to it are a few little letters. Just a couple letters in the process. So that means I want to take this 5 over 24, A to the fourth, B to the first, and write it as what?
30.
Something over 120, A to the fourth, B to the second. Now, you have choices. Slide over a little bit, Ernie, and pull up a little bit towards the top, a little bit tighter. If you could bring it in just a little bit more. Now, it's clear we have A to the fourth here, A to the fourth here. If we just multiplied by B to the first, we'd have B to the second. So I hope it's clear that I'm going to multiply by a B to the first and a B to the first. And now I need to take that 24 and make it what? A 120. So how many times will 24 go into 120? You want to try again? 24 into 120 would go 5? Because 6 times the 4 would give you 24. So we're going to put a 5 here and a 5 here. So your answer is 25B. Robert, where did the C? I didn't get there yet. I'm taking the first fraction. I'm just working in the first fraction. I still have the second one to do. Well, don't be so happy about it. I still have to take the second fraction that Robert was concerned about, sort of never being satisfied, and this is going to be something over 120, A to the fourth, B to the second, This is an a to the first. So what do I need to multiply times a to the first to get a to the fourth? A to the third is going to be multiplied. And how do I get from 30 to 120? A 4.
Wait, what about the b? B to the first, right?
Where did you see it? I'm in the second fraction. With a,
No, but you have a b squared down there.
and I have a b squared here.
Right.
Aren't those okay? Do I need to get any more b's here? Okay, if I take 120 a to the fourth, b to the second, and divide it by 30, a to the first, b to the second. So I have the b to the second over b to the second is a 1. The 120 over 30 gave me a 4. And what is a to the fourth over a to the first? A to the third. So this all comes out 4a to the third, correct? Now what I'm arguing, rather than doing this division, why not simply compare what I have here in this denominator with what I want in the LCD and ask what's missing? The Sesame Street approach. So I have an a to the fourth, or I have an a to the first, and I want an a to the fourth, so I need to multiply by a cubed. I have a 3 to the first, I have a 5 to the first, I have 2 to the first and want 2 to the third, so I need a 2 to the second. So I think that's 4a to the third, and this would look just like here. That's why I chose to do that. Now up here, Robert's c is now there. That's c to the first, or just c. Well, that's it. You changed them. Now, what would be the next logical thing to do? Why would you go through all this if you weren't going to add these? So, at some point, you anticipate you're going to be doing what? Instead of saying, let's slide over now, Ernie. Instead of saying you have these two fractions, you're going to say what? Add these two fractions, but first get an LCD. So if I replace the and by plus, what would then happen as we slide back? Well, you would say now, if I'm going to add these, which you weren't asked to do, but that would be the logical reason for doing what we just did, you would then say you have 25b plus 4a to the third, c, all over 120 a to the fourth, b to the second. Well, the question, is there anything that you can write this with a greatest common factor? Is there anything common to both these two terms? No. This is 5 times 5. This is 2 times 2. There's a b here, but not there. You're done. That would be the answer. Now, that was not the intent. It was just to stop at this point. I don't know how to read your looks. It's not as comfortable as I would like. Now, let's back up again. Let's slide over. Sandra.
Okay, so I see where you got the 128. Well, wait, where did you get the 25b for? Like, I know how you got the two different fractions, so how did you get it to want to add together? I don't think I'm saying it right.
Okay, let's come back to here, just to this point. You see how I combined these two to get, how I had these two new fractions.
Right.
Now, if I wanted to add them, wouldn't I take the intermediate step we practiced in Math 10 ad nauseum, where we said add the numerators and put it over the LCD.
Oh, okay.
Now slide over. That's why I had you do every one of those additions and subtractions with fractions with the intermediate step. So I could say, remember what we did back when? Now, that isn't always a memory that stays, but these two fractions were over the same denominator, so I can add the numerators, put over the common denominator, intermediate step, but here's a place where I can go no further. That was based on this argument I gave you many, many weeks back. I said if we had two fractions like a over 5 and b over 5, we know we could add the numerators and put it over the common denominator. That was our intermediate step, and it so happened that's as far as you could go. Exactly what we're doing here. So I'm trying to build on what we did in 10. And if you haven't figured this out yet, keep in mind that everything we've been doing with these fractions goes back to what we did in 10. And if I had questions about how to prime factor, I just jump back into the 6th lesson. Or if you're reducing fractions with primes, the 7th lesson. If you're adding, where you had to go ahead, I think it's the 11th review, where you had to find the LCDs, do everything I've done in this problem. The only difference is we didn't have letters. Now the argument that we make, if you understand what you did with arithmetic, then the structure we're doing here is exactly the same structure, but with some letters thrown in. And the segue, the movement from one to the other, is supposed to work for you because you saw us go through, as we slide back one more time, Ernie, to here, we went through this process so many times in Math 10. It's the same process. What's bothering you a little bit is I have letters thrown in. And that's just enough of a wrinkle to make it a bit uncomfortable. I'm hoping that doing it with numbers, you can handle this transition where we throw a few letters into the problem. So I'm going to leave that there. I'm going to walk back up front. Okay, that was a typical example. Obviously, some of them are a little bit easier because if I go back to the preceding page, I have a problem such as, and this is now looking at something like number 28, which I again need to cover part of what I don't want visible. And then another part that I don't want visible. There's my problem. This is number 32. Okay, about ready to get a couple rocks I can use. Hey, that worked better. Okay, let's look what we got there. Okay, we're going to come over to some space, Ernie, I have over here. Now, what are your directions here? This is number 32. Okay, I have 20h to the 5th, k to the 3rd, and 15h to the 2nd, and I have a k to the 1st. Now, in this case, I'm just asked to find an LCM, correct? We don't have them as denominators, but you can think of something like maybe a 1 over this and a 1 over this, if that makes you happier. We're just going to find the LCM, which if they were denominators, we'd call an LCD. So what am I going to do? First step. What are you going to tell me to do? Prime factor? Agreed? So what is 20 going to factor into with primes? 2 to the 1st, 5 to the 1st, I should say 2 to the 2nd, 5 to the 1st. Do we agree? And then I still had h to the 5th, k to the 3rd. Okay, what about the 15? 3 to the 1st, 5 to the 1st. The nice thing about these, we don't get big numbers very often. Now that I've said that, I'm sure that we'll hit something up in the 40s or 50s, but what's my next step? Any of the primes we see, we write down. 2s, 3s, and 5s, and any letters I see, write them down once. An H and a K. Now what do I search for? Highest exponent. So on the 2, I have 2 squared and what? Nothing else, so that's 2 to the 2nd. A 3 to the first. I have a 5 to the first. H is with a 5, highest exponent. The K is with a 3, highest exponent. Now that's supposed to be something that you can whip through and say, okay, got that. So what's the shortcut here? I would take the 4 times the 5, getting 20 times the 3 to get 60. H to the 5th, K to the 3rd. Do you have to do any more? No. You probably feel cheated because you're done that fast. Any question in that? Okay. The lack of questions scares me because I think you're going to walk out of here, sit down, and try one of these and say, I don't know what to do now. Okay, let's back up a little bit further. Just as a reminder, okay, that's not too bad. I can get that, so not quite there yet, Ernie. Still playing with cards. And I lost it totally. Okay, that, and this, and that, and... Okay, I've got 3 numbers, 26, 30, and 39, just as a reminder. We can do these 3 at a time, not just 2 at a time, correct? Now, I'm not asking you to go ahead and on these show your divisions. We did that to an extreme in Math 10. But look at the 26, the 30. So I have a 26, a 30, and a 39. Now, can we write those as a product of primes without doing the division? I hope. The 23 is the problem number, not the prime. So 26 is 2 times 13. Agreed? So 2 to the first, 13 to the first with a dot between them. The 30, we already found that, is 2 times 3 times 5 to the first, first, and first. And 39 is 3 to the first times 13 to the first. So what are my primes? 2, 3, 5, and 13, correct? So I'd write a 2, a 3, a 5, and a 13. And I think we have 1s all across the board, correct? So 1, 1, 1, 1. And so that's going to give me 30 times 13, which is 390. Is there any question there? Erica? Okay. I'll go with that. Daydreaming, but you're okay. Any question for anybody else in this one? Okay, let's come off there. Do you realize, now you're at this point, wait a minute, Ernie, just come back to there for a moment. Okay, if you were to think of where you are today, and think of where you were last semester, and if I took my Math 10 group that's in here at 8 o'clock, and the one I'm going to see at 11 o'clock, and I were to ask them to come in and look at the boards today, what do you think their reaction would be? My guess is they would look at what we've had on these boards, and they'd look at all that and say, no way. Okay? Totally blown away, totally intimidated, and you're sitting there and you haven't started screaming, you haven't run out of the room, and you're feeling rather laid back and not panicked and think you can do that. That's quite a transition in 7.5 weeks. Okay? You need to appreciate what you're comfortable with today and what you weren't comfortable with this point last semester. And the reason I bring that up, as you look at what I would be doing in an algebra class, you wouldn't see a whole lot of difference. There are so many times during this semester as I've watched the Math 70 presentations at 4 o'clock in the afternoon to check them out to see everything's working okay on the broadcast, that I have to ask myself which class I'm in, because it's so similar to what we've done in here. It just carries it a little bit further. So I don't think you're going to find the same sense of panic if you were to go into a 70 right now and look at what's happening there. If in doubt, just dial up one of the lectures on the internet. There are 60 of them. And just look at one of them and see if you're blown away in the first part. The homework I have in this set starts at number 7, and pretty much the odd-numbered problems all up to 27, skips a couple and ends up in 49. So it's not too bad. I'll try to get that on the list, but we need to close down here because another hour has gone by. I think of car talk, and you've wasted another hour. But as we close down, Ernie, with dire...